We're talking about the photoelectric effect, and the photoelectric effect is something that often only comes up later on in the year for matrics. But one of the things that you can do tonight is I've tried to set up the lesson so that you can take notes and actually learn it from scratch, so this should be useful. Whether or not you're watching it live or you're PVRing it or you're watching the highlights package, no problem. What I'm going to be doing is I'm going to be taking you right through the photoelectric effect and see where it goes. Well, let's go right back to the beginning, as is a good place to start. One of the things that I thought I would show you is where the photoelectric effect actually came from. Okay, the guy in the picture, most of you will know him, Albert Einstein. He won the Nobel Prize for a paper which he wrote in 1905. What he actually managed to figure out was why certain things were happening. This guy managed to figure out that light was a particle which carried energy. Now, that may not seem like a big deal, but he actually managed to figure out one of the major puzzles which was happening inside physics. He managed to figure out that light was traveling as a wave and as a particle. Now, not many proofs for particle existence had come along until this 1905 paper, and this is what won Einstein the Nobel Prize. So what we're going to do is we're going to take a look at the 2 points which he came up with in his famous paper. He told us that photons are the particles of light and that they contained energy called quanta, if you want to write that down. And if the photons contain enough energy, they can free electrons from atoms. Now, I've got a great video clip a little bit later on. We're actually going to show you that electrons can come off and we can actually physically see electrons leaving something, and this is a very nice graphical way of representing it. Okay, so how does the photoelectric effect actually happen? I'm going to break it up into a few steps. We're going to talk about the light particles coming in. We're going to talk about the way that they interact with the surface, and eventually we're going to have the ejection of electrons, but we'll come to that in a little bit. Okay, so let's start off with a challenge. Now, for those of you that are working with us, we're talking about the photoelectric effect. I'm going to use a light of 100 nanometers shining onto a surface of 4.3 electron volts. Now, that's a reference to its work function, the W0. Its work function is 4.3 electron volts. Now, that's zinc. Now, the reason that I've used zinc is because it's the same one that we've used inside our clip, and you can actually see what's going on. So I've got 100 nanometers, which is UV light, ultraviolet light, and it shines on a surface of 4.3 electron volts, and that's a reference to its work function, how much energy is required to release electrons. If you're not sure what I'm talking about, it's okay. I'm going to explain it in bits and pieces. So I'd like you to take this challenge question down, see if you can post a couple of answers on our Facebook page, maybe Twitter them through, and we'll see if any of your tweets are correct. So 100 nanometers is our wavelength of light. 4.3 electron volts is the work function, and I want you to calculate the velocity of the ejected electrons. So there's a couple of pieces to this. I'm going to break this down into 3 steps when you start to take a look at the photoelectric effect. A lot of equations involved and a lot of complications. So while you're busy taking this down, what I'm going to do is I'm going to break it up into those 3 parts. I have the light arriving, which was 100 nanometers, that UV light shining on the surface, the work function, and then eventually the kinetic energy which comes off in the velocity of the ejected electrons. All right, fantastic. I hope that you're working furiously away at that. If this is a new section, just wait for the show and we're going to work your way through it. Okay, so let's jump into how this actually happens. All right, well, I've got my light which shines on a surface. Now remember that Einstein managed to explain that these photons of light, these packets of energy of light which shine down, can be quantified. This means that I've got an amount of energy which comes with the light, and it comes in these little packets. The way that we can calculate the amount of energy inside them is using something called Planck's constant, and I've shown it on the screen here for you. 6,63 times 10 to the minus 34 joule seconds. That's a constant which is given to you during the exams, and if I multiply that by the frequency of the light, we can actually calculate how much energy that light has got. I just want to pause on that for a little bit. Planck's constant multiplied by the frequency of that wave, we can actually figure out how much energy this particle is actually delivering to our metal surface. Now we've got our electrons down at the bottom here. Remember, we're talking about the photoelectric effect. Photo, reference to light, and electric, we're talking about electrons which are moving. So what we're going to do is we're going to see how electrons come off the surface and where do they go once they've left the surface. Well, let's take a look at the next part. Well, Once the electrons have gained this energy, the photon of light has gone in there. You can see that my electron is busy moving off the surface. This W0 is the work function. This is how much energy. Remember I told you a little bit earlier on that zinc's work function was 4.3 electron volts. This is what I'm talking about. Work function is W0. And I've got W0 here, which is the energy required to pull this electron up to the surface. Now that requires a lot of energy, and that's the work function. So some of the energy which comes in is used to free the electron. Question is, how do I actually figure that out? Well, this is coming from the frequency of the light. Remember I told you that you could calculate the amount of energy by taking h times f, Planck's constant, multiplied by the frequency. I call the minimum frequency that I need to eject these electrons from the surface, I call this my threshold frequency. And the way to calculate it is here. My work function is equal to Planck's constant multiplied by F0, which is the threshold frequency. So one of the things that you can do is you can answer questions now about work function and threshold frequency. If I gave you the work function, you could calculate the threshold frequency. If I gave you the threshold frequency, you could find the work function. All right, now the threshold frequency is actually a really, really important thing because this tells me the minimum speed at which photons have to vibrate, or these waves rather, have to vibrate to free electrons from a surface. Now there definitely is a cutoff point. This word threshold means that there is a cutoff point. Now if I exceed that cutoff point, that means that I allow electrons to leave the surface. And what we're going to do is, in one of the slides which is coming up next, we're going to take a look at a video clip which actually shows us this in effect. But before I do that, what I'm going to do is I'm just going to show you where the electron goes. I've had my photon of light coming in, the electron has absorbed energy, and the work function has been used up, that amount of energy has been used up to free the electron, and now there's extra energy, which is K, standing for kinetic energy. What we're going to do is we're going to show you a short video clip of electrons being freed by UV light. Now, I want you to take a look. What the professor is going to explain to us is how much energy is required is actually shown by the frequency and wavelength of the light which he uses to shine on the metal surface. We're going to take a look at that video clip right now.
Well, in 1885, round about that period, a very interesting discovery was made by Heinrich Rudolf Hertz, the man who in fact proved the existence of radio waves. What he also did was he found an effect known as the photoelectric effect. And in our laboratory today, we can actually show a very simple experiment, a very classical experiment, if you like, on this particular effect. Here we have a typical Goldleaf Electroscope, and I'm sure most of you have seen Goldleaf Electroscopes in your time, but just to give a brief explanation, what happens is that if I charge the Goldleaf Electroscope with some electrical charge, a static charge, be it positive or negative, the gold leaf within the glass enclosure here will simply open up to indicate to us that such a charge exists. Now, what we're going to do is I'm going to impart upon this electroscope a negative charge, and for that I've got a nice piece of fur here and a glass rod, and we'll simply rub this rod thus, and with a bit of luck, and in a lot of cases physics experiments tend to fail, but let's hope that this one works quite nicely. You will see now that as I bring the rod to the electroscope, the gold leaf stands out very proud. There we are, we've got a nice charge on there, and that hopefully is a negative charge. Now, first of all, let's expose that negative charge, if you like, and our zinc plate. I'm going to expose the zinc to ordinary white light. There we go, from a good old torch. And as you see, absolutely nothing happens. Let's see if it has anything to do with the intensity, because it might well be. For this, I've now got one of these really high intensity lamps used in filming, as we have in the studio, and there we go, we switch it on. I've now applied a large amount of high amplitude, if you like, high brightness white light, and still nothing happens. Let's now put the ultraviolet light in place, and look what happens. Your gold leaf discharges. You can actually see the gold leaf dropping from the near horizontal position back to the vertical. Now, I imparted onto the zinc a negative charge, electrostatic charge. When we exposed the zinc to ordinary visible light from this torch, nothing happened. The gold leaf tended to stand out, and as we applied the light, nothing occurred. It stayed put until we put this shorter wavelength source of light, this ultraviolet light, which is at around about a wavelength of about 390 nanometers, if you like. We placed this, the source of light close to our zinc plate, and what in fact happened was that photons, very high energy photons from the ultraviolet source, struck the zinc plate and thus knocking off electrons. And so our negatively charged electrons were released, and of course discharging our Goldleaf electroscope.
Wow, fantastic. Thanks so much for that, Prof. I hope that you saw inside the video that he actually explained that if light has a short enough wavelength, and I hope that you remember from grade 10 that a short wavelength means a high frequency, that we've gone over the threshold frequency. We've got enough energy to get past the work function. And that's exactly what was happening inside the video. I had all these electrons nicely lined up on the surface of that electroscope, which was zinc, and it's zinc inside your work through example. And I've got the electrons actually leaving the photoelectrons actually leaving this electroscope. And we can actually see that because the leaf went down. The leaf discharged, showing us that electrons have actually left because of the UV light. Something else which was important to show was then when he was using a lower frequency, in other words, that white light from the torch, that nothing was happening. The frequency was too low, and this is a great example of something that they can ask you in an exam. If the frequency is too low, no photoelectrons will be ejected from it. What we're going to be doing is I'm going to be taking you through the mountain of equations which are on your equation sheet. I'm going to show you how to use them, how to pick the right one, because a lot of people say, oh, I don't know where to start. Okay, so I've listed a couple of the equations. I'm going to write them out with you, and we're going to see exactly what goes on here. Remember what I talked to you about, and I'm going to take a little bit of time in explaining these. If you want to write them down, it's entirely up to you. I'm going to be taking them down one by one. I'm going to be highlighting the important bits as I speak through them. Now, the first and most important one is that the energy of the photon is what goes in. Now, where that energy of the photon goes is entirely up to how much is used on the work function. So let's just highlight this as we go, because there's a lot of information here, and I want to make sure that people can follow even if they haven't done this section yet. So I told you that the energy of the photon, this is the energy of the light which is going in. I've got on the other side where the energy goes. I've got the work function is how much energy it takes to pull the electron off, and what's left over is how much is left over for kinetic energy. Now, you can change this equation exactly to suit your needs, and there's two major forms that I found. I found that energy of photon, because E is equal to HF of a photon, that's the basis of this, that if I find the energy of a photon, I can find it by saying Planck's constant multiplied by the frequency. So that's the energy which is going in. Where does the energy go? Well, it goes towards the work function, and you might recognize this before from grade 10, that kinetic energy is equal to half times by the mass times by the velocity squared. Now, this one is really, really tricky, because remember what you're doing is you're talking about the mass of an electron, and that should be a big hint towards solving our challenge question tonight. The mass of an electron is the mass of the object which we're actually accelerating. We can't talk about accelerating the surface, we don't know how heavy it is, but this is definitely that mass of an electron. Okay, well, now we know that K stands for the kinetic energy of these electrons. We're working our way through these. We know that energy of our photon is equal to HF. We use up our work function, and we're left with kinetic energy on the other side, and that's a half multiplied by the mv squared. So I know that I've got work function and I've got the kinetic energy over there, and that actually tells me how fast my electron is going. So if you're on this path, fantastic. The problem with what I did was I gave you not the frequency, but I gave you the wavelength. So the form of the equation which I'm going to use uses a little bit of grade 10 wave stuff. And never forget it. Go back and revise. That the velocity of a wave, in this case c, which is the speed of light, is equal to frequency multiplied by my wavelength. C is equal to frequency times lambda. Remember that that applies for any wave which is electromagnetic. That applies to light waves, to radio waves, to microwaves, infrared, even UV, which is our challenge question. So I've got my C, which is equal to speed of light, is equal to frequency times lambda. You don't have to go and find the frequency before you do your photoelectric. What I've done for you is I've shown you the formula when we've combined it all. I've swapped out frequency for C over lambda. I'm just going to highlight what I mean by that. A lot of people are going to get a little bit confused here. C over lambda is equal to frequency. That's all that I've done in that equation. So H times by frequency, in other words, C over lambda, which is way more useful, is equal to my work function plus a half times my mass times velocity squared. Something else which is going to bother a lot of learners at home is how to work with electron volts. I'm finding that a lot of people say, work function, fantastic, you gave it to us, it was 4.3 electron volts, I'm going to substitute it in there. You cannot. And I'm pretty sure that a lot of people on the Facebook page are actually saying, what is 4.3 electron volts? That's one of the things that I'm fairly sure that's coming through. I'm finding that C over lambda is equal to work function, and my work function has got to be in joules. I'm not sure if any of the viewers at home have started answering. Have they, Indy?
They have indeed. Would you want answers?
Well, not quite yet.
Not yet. You just want to know if they're listening.
Absolutely.
Okay.
I want to see if people are asking questions, what they're confused about, and we're going to move on from there.
Okay, guys, if there is anything that you are confused about regarding the question, let me know now, so when we do answer the question, we can go over it with Phil.
Fantastic. And
Cool.
that'll be answered in our third part of our show.
Yes, exactly.
Okay. Fantastic. Okay, so we're getting back to this. We've identified which one out of these three is most suitable for our answer. Well, I've got the speed of light. I always have h, which is Planck's constant, 6,63 times 10 to the minus 34. That was given earlier on in the show, and it's always on your information sheet. So c, 3 times 10 to the 8 meters per second, which is the speed of light. Another constant which is given to us. The wavelength, which was 100 nanometers. Now, please don't substitute 100 in there. I'm going to show you why in a moment. My work function, can't substitute in the electron volts. Remember, this is a challenge question. A lot of you are not going to get this correctly. I've got my mass of an electron. So each one of these is going to require you to think heavily. I want you to use this equation, and we're going to work through it together. One of the big hurdles that you're going to find is using electron volts. Now, not all of you have to do this during exams, but I'm going to show you how to change from electron volts into joules. And then we're going to get on to the actual solution for our question. If I take electron volts and I multiply by the charge on an electron, I get back to joules. That's quite an important thing to know. The reason that I do this is 4.3 is a much nicer number to deal with than the actual amount of energy. The amount of energy is so small, so minute that I can't actually work with it. The amount of joules is very, very small. So let's actually take a look and see how the conversion worked. If I take a look here, I've got 4.6, apologies, sorry there, 4.6 times 1.6 times 10 to the negative 19. We've got our conversion back into our joules. So I'm working with 4.6 electron volts here. I multiply by the charge on an electron, and I'm changing it into joules. I hope that everyone can see that. 4.6, I've multiplied by charge on an electron. That will get me into the joules. Now let's use our information here, and let's work forward. Okay, so I've got my original equation. I've broken it up into two pieces because they're so large. I could take this and put it back on there, but you can see that that doesn't fit onto the screen. So I hope that you'll bear with me that it actually does fit onto the screen when we break it into two parts. Okay, so I take my Planck's constant. 6.63 times 10 to the minus 34. There it is. I take my Planck's constant. Now, what I'm going to do is I'm going to substitute in the speed of light, which is c. So 3 times 10 to the 8. Here's our wavelength. A lot of people don't know to do this. 100 nanometers. If I take 100 nanometers and I put it in there, what I'm going to find is that 100 nanometers over here is going to give us 100 times 10 to the negative 9. Nano means times 10 to the negative 9. And that's something a lot of people don't actually know yet. Here's our work function that we worked out over here. I've got my work function here, and let's just move it over, make sure that everyone can see it at home, right? Because I think I'm fairly close to the side here. I've got 7,36 times 10 to the negative 19. Let's just move over our highlighting because that should actually fit in there. There we go. Right, and that's the amount which I substituted inside there. And I add to this a half times, and a lot of people don't know where this number comes from. This is a number which people don't actually know that they've got. I've got my electron volts changed into joules over here. This is the other constant which is given to you as the mass of an electron. 9,1 times 10 to the minus 31. And that's kilograms. This is how small an electron is multiplied by V squared. That V is what I'm after. So if I take 9.1, sorry, let's just make sure that we're highlighting there. Let's just move that off. All right, if I take 9.1, 1 times 10 to the minus 31, and I multiply that through and I start solving, I'm going to show you how to manipulate this because this maths is very, very complicated. I'm going to show you the fully manipulated part and we're going to see. So on my next slide, I've done exactly that for you. All right, so I've blown it up nice and big. So what I've shown you is that I've got my fully worked out answer on the left minus my work function over half times my mass of my electron. And that was equal to V squared. So that was my manipulation. I found V squared on its own. The only thing which I've got to do left is actually to find V. And I've got to find V by square rooting the whole lot. Now, some of you might find a slightly different answer to this. And most of the reason behind that is because of rounding halfway through. Some of you have kept it in your calculator, some of you haven't. That's no problem. If I put it in as such, I'm going to get a velocity of this, and we're going to find a velocity in excess of 1,000,000 meters per second. That's unbelievable. Very, very fast. Okay? So this is starting to get like into physics breaking territory, and you'll actually find that electrons don't really do this in real life. What happens is as they start approaching the speed of light or exceeding it even, which is not actually possible, they'll start getting heavier. This mass won't actually apply anymore. I want to see if any of the viewers at home have managed to get an answer similar to this one.
Okay, well, let me have a look. I'm going to be honest with you, Phil, here, but don't be upset, because it's got nothing to do with your teaching.
Okay.
A few of the learners are a bit confused, and I was wondering
okay.
if I could ask you a few questions regarding to this question now.
Absolutely.
Before we move on. Let's see. Do you want to know what is C?
Ah, very good question.
Yeah.
Okay. All right. We did explain it very briefly early on, but I kind of assumed things, and you can never assume things. Okay. I'm going to go back to C. Let's actually make a little bit of space down here at the bottom. Let's explain what C is, because that's a value which people don't actually know about. The reason that I used it was that I had C is equal to frequency of a wave times by lambda. Now, C was the thing that people weren't sure about. The equation that people are used to from grade 10 is actually V is equal to frequency lambda. Now, why have I chosen to take C in place of V? Well, C is a particular velocity because V stands for velocity. Now, in this case, this is the speed of the light waves. So this is the speed of light, and that's a constant given to you on your equation sheet, which is 3, 0 times 10 to the power 8 meters per second. Now, that is an unbelievably high speed, but remember we're talking about the speed of light. This speed will get you 7.5 times around the world in 1 second. It's unbelievably quick. Even at this speed, it takes 8.3 minutes for light rays to get from the sun to us. Something else very interesting, something which I like to give people as a challenge, is how far away is the sun from us if it takes 8.3 minutes, in other words, 8 minutes and 20 seconds to get you at this speed. Something that you can do if you're looking for a little bit of time and a little bit of a challenge. I hope that answers that question.
I hope so too, Phil. Okay, here's another one from Sophia. Why can't we use the NM as 100? Why not?
Sorry?
She says, why we can't use the NM as 100? Why
the
not?
nanometers.
Yes.
Okay,
yes,
fantastic.
Yes.
All right. Very good question. This is one of the problems that we actually bump into a lot when we're working with photoelectric, when we're working with our light waves. I'm going to talk to you about this guy, lambda, which is our wavelength. I told you earlier that lambda was equal to 100 nanometers. If I've got 100 nanometers and I'm substituting it into this equation, something which you'll notice, especially in your constant C, and I'm going to highlight this because this is very, very important. My speed is in meters per second. I cannot work in nanometers. This is why I cannot use the nm or nanometers. What nano means is 1 billionth. I could take 100 and divide it by a billion, but that's a real pain in the butt. So what I'm going to do is I'm going to take 100 and I'm going to use times 10 to the negative 9. So let's give ourselves a little bit of a space there, and let's actually work our way through there. So instead of saying 100, I cannot use 100. Let's use 100 multiplied by 10 to the negative 9. What that does for us is it makes this into meters. And remember, because I've got a speed in meters per second, I've got to use a wavelength which is in meters, and that's why I can't use that. So that explains where C came from and why I can't use nanometers. Very, very important. Now, this is something people have probably forgotten from grade 10, but I've got to work in SI, or Scientific International Units.
Okay, here's another one from Maro Ping.
Good.
How do we get the mass of the electron?
Ah, very good question as well. A lot of people are asking about these constants. Now, they're not very familiar to you. I want you to look for the following thing. If you find on your equation sheet, this is the one that you're going to look for. Right, let's just make sure that we can write on there. Sorry, let's just move that out of the way. So, if I've got a mass of an electron, oh, we're struggling there. I actually want to show you the mass of the electron. There we go, the mass of an electron. This is something which is actually a constant on your equation sheet. The mass of an electron is a known mass. It does change with the speed, but I don't want you to worry about that. Is that mass of an electron is 9,11 times 10 to the minus 31 kilograms. That is the mass of an electron. This is given to you. Either it's in the question or it's on your data sheet, but this is a constant which you should be used to and they should actually give to you. This is something which I need if I'm going to find the velocity of an electron.